Today we're going to take a look at what's called the area of the surface of revolution. Now this is closely related to our volumes of revolution that we've seen in the past, so we're actually going to start out with a picture that looks quite a bit like what we've seen. Let's say that we have this region here, and again it's kind of our square root thing that we've seen in the past. And again we're going to revolve this around the some axis. Now this time we're not going to think about this as a solid shape sweeping out a volume. We're going to just think about this as a single curve sweeping it out. So we'd still get this type of shape like this, but we're not talking about the volume of that. The question is just what is the area of the surface of that kind of bell shape? All right, just like in the past, what we're going to do is we're going to take a look at a very small piece of it and see if we can come up with the formula. So imagine this. Imagine if I only pick a small region here to look at. Right, a very small piece, and we rotate that around. What shape would we end up with there if that's rotated around? It's going to kind of do that like this. What you end up with is kind of like a ribbon. So you'd have a piece up here that's rotated around like this. Oh, come on, messed up. Kind of like that. So you get this, just a sliver of this, right? Just an outside surface of it. So the question is, what's the area of this shape right here? Now remember, we have our axis of rotation kind of running through the middle there like that. Okay, so, well, here's what you do. Imagine if you could take this ribbon, whatever it is, take a pair of scissors and cut it. And then if you were to unroll that, the shape you would actually get would be a long rectangle. The good news is we know how to find the area of a rectangle. Now if you take a look at this piece here, what is that length there? Now that length here is what I have drawn right there, which would end up being something like either the top or the bottom of that rectangle, of course. What is that? Well, we said that that was a small piece of the curve or a small piece of the arc length. So this is a very small piece of the length of that curve. What's the length of this side? Well, this side, as you just pick one side or the other, you get this circle here. Now the circle there is going to be determined by whatever the radius of that circle is. So you think about it right here, if I kind of drew that down, that would be the radius of that circle. Well, we know the length of a circle is 2 pi r. Well, let's see. The radius here, now notice in this case, if we're measuring from the x-axis, the radius here would just be a function of x. So in this case, generally this radius, since it's going to change as you move across, depending on which way you're moving, either that's going to be a function of x or a function of y. All right, let's just kind of put all the pieces together and see if we can come up with a formula. So this piece here, this was a very small piece of the surface area. So DSA, surface area. So a very small piece of the surface area is the area of this ribbon, length times width. So this is going to be 2 pi r ds. Well, remember the way that I have this particular thing set up, I kind of have an r of x, but r is either going to be a function of x or y, but that's a function of s right now. Well, we saw from last lecture that we could represent ds either being a function of x or a function of y by writing it like this. I'm going to do it as a function of x for this first one. 1 plus dy dx squared dx. Right? Remember that was our ds element from last time, or if we had solved for y as a function of y. So here I'm assuming r is a function of x. So I'm going to write one more step here just to make sure we can see it. So that's going to be some radius function, 1 plus dy dx squared dx. Ooh, ugly, but there we go. There we have expression all in x on this side. So that's for a very small strip of the surface area. If I want the entire surface area, all I got to do is add this up. And since I defined everything in terms of x's, I got to add them up in the x direction. So we're going to integrate integral 2 pi r of x 1 plus dy dx squared dx. So of course we integrate ds, a, we get sa. On this side, 2 pi is a constant, I can pull that out. So r of x square root 1 plus dy dx squared dx. And since we're integrating in the x direction, generally we want to go over some regions, so let's just call this region A to B. Okay, there you go. There's your surface area formula. Now we could have done the entire thing the other way. So this 2 pi, so C to D, r of y, 1 plus dx dy squared dy, right? That would be the whole thing if I just drew the picture in the other direction. So here we go. There's your two formulas for surface area, and you're thinking, oh my goodness, that's horrible. Because I just did the homework on arc length, and that piece there's the arc length, and by adding this extra function out front, we made it even more complicated, and I could barely do the homework for the arc length. Well, believe it or not, even though the formula here is more complicated, this integral is actually easier to do most of the time. Because with just our, I'm gonna erase this, I'm gonna put it back. If you just look at just our arc length formula, we got this function stuck inside the radical, which one of our go-to methods for integrating is Udu Type Substitution. I don't have anything really on the outside to help me substitute, but now that I have this other function on the inside, there's a really good chance to do that type of Udu substitution. Because think about it, if we're going about either the x-axis or the y-axis, then these two functions here end up just being the function itself. And over there you have the derivative function squared, which means it's going to be pretty closely related to this out here. All right, let's just try a quick example, because these are actually, no, it doesn't look like it, are actually easier to do than the arc length. So there's our derivation out of the way. So find the surface area created revolving, let's do something easy. Y is equal to x squared, x cubed, about the x-axis on the interval, I don't know, 0 to 1. Make it real easy. Okay, so let's see if we can put this together. Again, we're just using one of these two formulas. Since here we have y as a function of x, we're most likely going to be using this formula here. So you don't necessarily need to do a quick little sketch, but just so you can kind of see what's happening. Since I'm going from 0 to 1, I know my curve kind of looks like this. And I'm going about the x-axis. So from here, you can see that that distance there would be your radius, and that's going to be a y function, right? Y equals that. Now, since we're measuring from the x-axis, that distance right there is exactly y equals x cubed, right? There's your function of x. If we were measuring from some off-axis, then you're going to have to adjust it a little bit. So let's put it in here. So our surface area is going to be 2 pi, integral from 0 to 1. Our radius function here is x cubed, so that's x cubed. Square root 1 plus, well, that's easy enough. The derivative of x cubed would be 3x squared dx. 2 pi, 0 to 1, x cubed, square root of 1 plus 9x to the 4th dx. Okay, so there's what we have to integrate. Again, Udu substitutions are going to come into play here quite a bit. And notice if I let the stuff inside the radical be Ru, du would be 36x to the 3rd dx. And that's basically what I have right here. It's just off by a constant. So depending on how you were showed this originally, I'm going to put the 36 I need right there, but I can't just put it on the inside. I have to divide by it to compensate. So now this exactly becomes, on the outside, that's going to be pi over 18. The integral, now I'm going to leave the bounds off because I'm going to change the u's here. This is going to be the square root of u, and 36x cubed dx, all of that is du. So our surface area, pi over 18, the integral of u to the 1/2 du. Okay, so easy enough to integrate, add 1 to the power, divide by the power. So our surface area, add 1 to the power, we get 3/2, so 2/3 out front, so pi over 18. We end up with 2/3 u to the 3/2 evaluated, not evaluated, sorry. Say pi over 18 times 2/3, I could have simplified that. What was u again? U was 1 plus 9x to the 4th, so 1 plus 9x to the 4th to the 3/2, now evaluated from 0 to 1. All right, let's, actually we can do one more step before I go too far. What are you doing? If you pull the 2/3 out front, what would we end up with? The 2, that'd be 9 times 3, so we get pi over 27 out front. 1 plus 9x to the 4th. 3/2 evaluated from 0 to 1. So top endpoint minus bottom endpoint, we're out of this. This one's going to be pretty easy. So pi over 27. Top endpoint, you get a 1 in there. That's going to be 10 to the 3/2. I don't know what that is. Minus when you plug 0 in there, 1 to the 3/2 would be 1. All right, so the arithmetic for that one was very, very straightforward. So notice, even though the formula was more complicated here, because we have that extra function out front, it lends it to be able to do some type of substitution, which actually makes these a little bit easier to do. So surface area, it is just a formula. You're basically finding the area of one little ribbon as you rotate around whatever your axis of rotation is.